Okay, thanks. So I'm Vered from Maryland University, and I'm presenting this work that was mostly done by Max Glockner from TU Darmstadt. I couldn't be here. And it's joint work with Yoav Goldberg. So we worked on, and it's about breaking NLI systems. So we worked with the SNLI dataset, which is currently the largest dataset for natural language inference or recognizing textual entailment. So it consists of pairs of sentences, a premise and a hypothesis, which are annotated to the semantic relations between them. So the premises were originally image captions, so they describe physical scenes, and the hypotheses were generated by crowdsourcing workers. That then, for example, a premise, an example premise is a street performer is doing his act for kids, and then the hypothesis, a person performing for children on the street, would be entailed because it conveys the same information, but not more information than the premise. A juggler entertaining a group of children on the street would be considered neutral because we don't know for sure that the street performer is specifically a juggler, but it may be. And a magician performing for an audience in a nightclub is considered contradicting because there is an assumption in this data set that the premise and the hypothesis must describe the same event, and these two describe different events. So since its release, the release of SNLI a few years ago, there has been a lot of end-to-end neural models developed on SNLI, and they usually follow either one of these approaches, sentence encoding models or attention-based models. So sentence encoding models, they encode each of the sentences separately, the premise and the hypothesis, using some kind of encoder, usually RNN-based. And then there is some step of extracting features from these vector representations, combining them, and feeding them into a classifier that predicts the label entailment, neutral, or contradiction. And in attention-based models, while encoding the hypothesis, the encoder can also access the words from the premise and attend to them. And this is very similar to word alignment, which was common in the traditional RTE systems. So for all these systems, the only lexical knowledge they have access to comes from the pre-trained word embeddings. So this is very fuzzy distributional lexical knowledge. And this is very different from the traditional RTE systems that used to leverage a lot of lexical resources, such as WordNet. Yet the state-of-the-art systems exceed human performance on SNLI. But we have to be a bit suspicious about that. We were recently told by several papers that this mostly happens due to learning very easy clues on the dataset rather than solving this very difficult task. So in this work, our question was, do neural NLI models implicitly learn lexical semantic relations? Because they seem to be doing something, even without this lexical knowledge. So to answer this question, we created a new test set. And the premises in the test set are basically just premises taken from the SNLI training set. And the hypotheses were generated by replacing a single term W in the premise with a related term W prime. And we've also made sure that these W prime words are both in the SNLI vocabulary and in the pre-trained word embeddings. So it's not new words. Then we crowdsourced the labels. We got mostly contradictions. Here are some examples. So the man is holding a saxophone contradicts the man is holding an electric guitar. A little girl is very sad entails a little girl is very unhappy. And a couple drinking wine is neutral with a couple drinking champagne. So these are very, very simple examples, much simpler than the original dataset. We evaluated 3 representative models on our test set. So these are the residual stack encoder, which is an RNN-based sentence encoding model, eSIM, which is also RNN-based, that also uses attention, and the decomposable attention model, that's an attention-based model without an RNN. So we trained them on the SNLI training set, and then we test them both on the original test set and on the new test set. And in the paper, we also have experiments with enhancing the training data with additional existing data sets. So first of all, the results, can neural NLI models recognize lexical inferences? So generally not so well. As you can see, all three models, they perform very well on SNLI, but then there's a dramatic drop in performance on the new test set. As a sanity check, we also evaluated the two models that have access to WordNet on our test set. So one of them is the key model, and the other one is a simple baseline that only classifies the sentences based on the WordNet relation between the original word and the word that we replaced in the hypothesis. So both of them reach mid-80s in accuracy, as opposed to the best neural model that achieves 65.6. So the test set is generally solvable using WordNet, but the end-to-end neural models don't seem to learn this knowledge on their own. So we also analyzed what do neural NLI models learn with respect to lexical semantic relations. So the first analysis was about word similarity. So what we found is that models tend to err more on contradicting word pairs that have similar embeddings. So for example, it's very likely that a model would predict that a man starts his day in India entails a man starts his day in Malaysia, which is incorrect. But this happens because India and Malaysia have similar embeddings. And this especially happens in models that don't update the word embeddings, because that's basically what they're relying on. So here's an example with a decomposable attention model that doesn't update the word embeddings. And what we see here is the accuracy on a subset of the contradicting pairs in our test set. And the x-axis is the cosine similarity score between the original word in the premise and the word that we replaced it with in the hypothesis. So the more similar these words are, the less accurate the model is on these pairs. The second analysis is with respect to frequency in training. So for models that do update the word embeddings, we can expect them to associate specific word replacement pairs to a label if they appear enough times with this label. So one of the most common examples in the SNLI training set is the word man in the premise and the word woman in the hypothesis appearing in contradicting sentences, which are generally probably similar to each other otherwise. So the models just learn that men and women indicate contradiction. So what we see here is, again, here is the accuracy of the EC model that updates the word embeddings. And again, it's on a subset of the contradicting pairs from the test set. And the x-axis here is the number of times that this specific word and replacement pairs appeared in contradicting examples in the training set. So the more they appear, the more the model becomes accurate on these examples, and up to the point of 98.5% in accuracy on pairs that appeared at least 100 times. So generally, it can learn specific pairs of with lexical semantic relations, but it has to observe them in the training set, which is not an efficient way to learn lexical inferences. So to recap, I presented a new NLI test set that evaluates systems' ability to make very simple lexical inferences. And we show that the state-of-the-art systems perform poorly on the test set, which is probably due to their limited generalization ability. And we suggest to use this test set in addition to the SNLI test set as a means of estimating how well a system does on this particular task of recognizing lexical inferences. Thank you.
Thank you. Any questions? Okay, so perhaps, oh, there is one there, the far back. Oh, there is also one here. Okay, so maybe you can go off to the back.
There was things like WordNet were incredibly popular a few years ago, and you don't see them mentioned much anymore. And I wonder, do you think that that's a mistake, that the lexical resources plus modern methods are better together, or do you think it's just the modern methods need to be tweaked a little bit, and then we no longer need the lexical resources?
That's a very good question. I actually do think that they are needed, and I think they would be helpful. There is one work that did that. I think it was presented here at the conference. The key model that I presented as a WordNet informed model, they achieved a small improvement on the SNLI test set and a much better improvement, much larger improvement on our test set, because the SNLI test set just doesn't require a lot of lexical knowledge. So that's one of the problems. I think there are a lot of people trying to incorporate WordNet knowledge into these neural models, including myself. It's just very hard to do for multiple reasons. I don't think it's because these models are inherently stronger and that they obviate the need of these lexical resources.
Please state your name and affiliation, please.
Hey, thank you for the great talk. This is really interesting work. I have a question about the new test set. That it seems that it's not balanced in terms of the classes. When you conducted the analysis of the previously trained models, did you recalibrate the per class biases?
No, we haven't. It may be a problem, I agree, but it's just that the examples are so much simpler than the original examples that we expected it to do better than the like the general prior probability for the class labels in the data set. But we haven't done that.
Okay, thank you.
Other questions? So I have one too. So coming back to classical methods, I think is the name you called it. So there were a bunch of other methods, right, that were data-driven back in the old days. And you know, some of them, in some respects, did better than WordNet. I mean, certainly had more coverage. Do you think that that the current models that are used, well, essentially obviate at least these type of all data-driven? I'm thinking, you know, about things like DIRT, say, or things like that, because you know, we heard just in a previous talk, right, about the fact that you can just use very simple distributional features, and that sometimes they, you know, can. So I was wondering if you tried that, and what's your opinion from your experience on using these kind of methods? So
I haven't. It's hard to tell because nobody evaluates the neural models on the old data sets and or the traditional methods on the new data sets. So it's hard to tell exactly, but my intuition is that it doesn't obviate all these methods. Probably some of them, the ones that are based on similarity, they're probably already captured in the embeddings and the neural network. We know that neural networks learn these things very well. But I think it's going to be very helpful to look back at the papers from, I don't know, 10 years ago and try to incorporate these features back into the neural models if we find a way to do that, because I do think it's complementary.
Okay, thank you. Okay, so time for last question.
Hi, I'm Matt Gardner. I'm from the Allen Institute for Artificial Intelligence. I guess I kind of read this work as a stinging indictment of the whole paradigm of build a large data set, split that data set into train and test, because it sure looks like we're not really testing the generalization of our models. Am I being too pessimistic here?
No, I'm with you on that. I tend to say that the models do some kind of an overfitting, and people always correct me and tell me overfitting is when you get good performance on the training set and bad performance on the test set. But I just think that the test set, the distribution is way too similar to the training set. So our models do very well on everything that's similar to what it was trained on. But then once we try to deviate on very, very simple examples that are just slightly different, then we show that they're not actually solving the general task of entailment, which I think is much harder than that. And yeah.
Okay, thank you. Let's thank the speaker again. Sorry, we're out of time. And this concludes the session.